Hi again. So now that we've returned to sampling distributions and seen the models, the formulas or models that we get as long as the conditions are met, we can now use these models to go back and do inference again. So we're going to do inference again, but this time use the formulas. So really it's just two different methods. There's a simulation method and there's a method with the model, and they have pluses and minuses to both, right? But I want you to be exposed and aware of both methods, okay? So let's see what we've got here. So inference with theoretical models. So we've seen from the central limit theorem that when the conditions are met, of course, we can use theoretical models for both means and proportions. And that's what we were doing in the last section, using the normal distribution, right? We can, if these conditions are met, then we can use the normal calculator. And so these are the models we saw, and these are from that conditions and models page. But we saw that p hat, sample proportions are distributed normally with a mean of p and a standard error of square root pq over n. And for means, we use this model. X bar, so sample means, are distributed as a normal distribution with a mean of mu, the original population mean, a standard error of sigma over square root of n, okay? And we've used these to find probabilities for a sampling distribution. Okay, but now remember we're taking away, we don't know the population, and so we're going to see how we can do inference with these models, okay? There is one caveat here. So this normal distribution for a mean is really only used in certain circumstances. Let me go back to purple here. So for means, this model only really works well if either sigma is known or if the sample size is large, okay? Here you can see there's one unknown, which is p, and we have our sample size n. But here we actually have two different unknowns, so that increases the amount of variation we have. So if we knew sigma, we could use this normal distribution, and some courses go into that kind of calculation. But that's kind of unrealistic expectation. If we don't know the mean, why would we know the standard deviation? So in practice, we use a different distribution for means. So we usually use the student's t distribution for inference with means, okay? So I want to show you this distribution just so that you're aware of it. We're not going to do much in depth with it, but just want you to be aware that it exists. If you take more statistics, you'll probably run into it, okay? It's also great to know that there are just many, many distributions. We're mostly using the normal distribution in this class, okay? So I'm going to show you a little bit about the t distribution. What it does is it gives us a different shape depending on the sample size, okay? And there's one input to the distribution. The input is called the degrees of freedom, which are n minus 1, okay? So we're going to go to Staplet, and I'll show you, I've got a screenshot of the Staplet app, so let's just go ahead and go there. And you can go there and play around with me. So just like the normal calculator, this is very similar, but it's a t distribution instead. It's set up very similarly to calculate an area or a value, okay? And then the input are the degrees of freedom. So let's say we had two data points, n minus 1, 2 minus 1 would be 1. This is the smallest it can be. So I want to plot distribution and show you what it looks like. Isn't that interesting? So it is unimodal, kind of bell-shaped, but it's more spread out and wider at the tails, right? In a normal distribution, you're getting down to the x-axis at about 3 or a little before, and then here this is way past 6, okay? So what it does is it puts more area in the tails for smaller sample sizes, okay? So that's why this is good for smaller sample sizes. You can also check this plot normal distribution, and then you can see the comparison. I should have done that first, because here you can see where the normal curve comes down, yeah, just after 3, and compare that with the t, okay? So we could calculate values, but we're not really going to do that. I just want to show you what the t distribution looks like, just so you're aware of different distributions. And so let me go back to the notes here for a second. Okay, let me move this up. Okay, great. So here's the screenshot of what we just did. The t-distribution is the solid line, and the normal is the dotted line is the normal. So this is kind of what I was just saying. Notice the sample size. When the sample size is very small, the tails for the t-distribution are much wider and longer. Okay, they're kind of fatter tails. Okay, great. Let's try another sample size. I gotta refresh my memory what I put on here. Let's try 10. So we actually would have 11 data values, since we always have one less degree of freedom. Interesting, huh? And you can try some values in the middle, and you can see it just gradually gets closer and closer to the normal curve. Okay, let's go back to the notes. So we've got this on here as well. Okay, so we have degrees of freedom 10. As the sample size increases, the t-distribution does approach a normal distribution. That's also why we can use a normal distribution for a large sample size, because the t and normal are basically the same. Okay, so in our class, moving forward, we're going to do inference for a single proportion with the normal distribution. Okay, so we're not going to go into means like we did with simulation. We're going to do the theoretical part just for proportions. Okay. In a single proportion, we're not going to go in depth into the difference of proportions. But if you take Stats 2, you can do that. So I just want you to be aware. It's good to be aware that there are many different distributions used for different situations. Okay, and of course you can learn all about that in Stats 2, or maybe you take another statistics class in the future. Okay, I'll see you in the next video where we'll start confidence intervals for a proportion. See you then.